Hi everyone, so we've been talking about light is both a wave and a particle. You've just completed determining the energy of either the quanta of light or photon while using Planck's constant. We are now going to talk about what is happening in the atom for the light to be emitted. Have you ever wondered how light is produced in a neon sign? Yes, I have too. This process can be explained again by the wave model of light. The light of a neon sign is produced by passing electricity through a tube filled with neon gas. Neon's atoms in the tube absorb energy and become excited. These excited atoms return to their stable state by emitting light to release energy. The light emitted by the neon is then passed through a glass prism and the atomic emission spectra is produced, which is what we see on the right-hand side. This process can be seen here with hydrogen. There is a tube, which is right here, that has electricity running through it. It excites the atoms in the tube, and the light goes through a prism to reveal the atomic emission spectra, right? Just like we have done with white light with a prism. The atomic emission spectra of an atom is the set of frequencies of the atomic waves emitted by atoms of the element. Every element will have their own emission spectra and can be used to identify the element. This also means that only specific frequencies are related to the energy emitted by the element. Scientists had expected to observe the emission of a continuous series of colors as excited electrons lost energy. In an absorption spectrum of an element, they will absorb the same specific frequencies of light they emit. In an absorption spectrum, the absorbed frequencies appear as black lines. By comparing the black lines to the emission spectra of elements, science can determine the composition of the outer layers of stars. Let's compare the emission and absorption spectra of neon. Here are the emission and absorption spectrum of helium. As we can see in the top, there are sections where there are lines missing. The bottom has the emission spectrum of helium like we spoke about earlier. How are they related to one another? They happen to be the opposites of one another. As we can see in the absorption spectrum, the black lines are exactly in the places where the emission spectrum is. So what is happening to the atom for it to emit light? Let's talk about two things first. One is something called the ground state, and the other one is called an excited state. When you hear the word ground, what do you think of? The floor? Perfect, right? When something is on the ground, we know it's at the bottom of the room. So when an atom is in its ground state, it is the lowest allowed energy state of an atom. When we hear the word excited, we know it's someone who is happy, so we know they have a lot of energy, right? So an atom that's in an excited state is an atom that has a lot of energy and wants to do something with it. To lose the energy, an atom has energy that needs to be released, and it is released as a photon. Let's look at a diagram of two Bohr models for what happens when an atom goes from a ground state to an excited state. As we know, absorption is when energy is being taken into the atom, and emission is when it is going to emit some type of energy. So let's draw the diagram for an absorption. Right, so we have our electron in its ground state. From here, energy is going to come in and is going to make this atom excited. So our atom is going to end up going up to a higher energy level. Now that we have our electron at a higher energy level, it has a potential of doing something because it has a lot of energy. So now that my electron is at its higher energy level, for it to go back down to the ground state, it is going to release some type of energy. right? This energy happens to actually be a photon. And our electron goes from our excited state back to its ground state. So tomorrow in class, I will be doing a quick demo on this, as well as having you complete a lab on it as well. So I hope you have a nice night, and I will see you all when I see you.